All right, another skill you need to know is to determine percent composition of a compound. So if you have a compound like sodium chloride, you've got to be able to determine what percentage of this compound is sodium and what percentage is chlorine. And you do that using molar mass ratios. Okay, you know how to do this. So let's say you are wondering what is the percentage of correct answers you got if you had 18 correct out of 25, right? You know that you take the amount correct and you divide it by the total possible. It's the same principle. Only now you're looking at the percent of an element in a compound. And so you're going to consider the molar mass of the element divided by the total molar mass of the compound times 100. So for example, let's look at the percent composition of sodium in sodium nitrate. You already know how to calculate the total molar mass of sodium nitrate, right? Which is the molar mass of sodium plus the molar mass of nitrogen plus 3 times the molar mass of oxygen, giving you a total molar mass of 84.967 grams per mole. So, if you want to know the percent of sodium in that compound, you take the molar mass of sodium and you divide it by the total mass of the compound times 100. And you get that the percent sodium in sodium nitrate is 27.05%. We can do the same thing to figure out the amount of nitrogen in sodium nitrate. So we take the molar mass of nitrogen divided by the total molar mass of the compound times 100, and we get that there is 16.49% nitrogen in this compound. Similarly, we can do this math with oxygen. What's the percentage of oxygen in sodium nitrate? So we have a total of 47.997 grams for every mole of compound of oxygen, and a total of 84 grams per mole of compound, and we can calculate that oxygen is 56.49%. All right? So you can do this. This is not difficult math. You're just taking math you already know how to do and you're applying it in chemistry. I know you can do this. So let's do a couple of examples. This first one, calculate the percent composition of silver nitrate. So what do you already know, right? You know the chemical formula for silver nitrate. And you know the masses of each element, and you can calculate the total mass of the compound. All right, so, and then we can figure out the percent mass of each element. So why don't we do that? The molar mass of sodium sulfate is equal to 2 times 107.87 grams for silver plus 32.06 grams for sulfur plus 4 times 15.999 grams of oxygen for a total of 311.76 grams. So now we can easily figure out the percent of silver in this compound, right? We know that there are 2 silvers, and so the total mass of silver from 2 of those would be 215.74 grams. And we know the total mass of the compound is 311.76 grams, right, times 100%. Will give us 69.2% of silver. Now let's figure out the percentage of sulfur. All right, we know that sulfur has a molar mass of 32.06 grams. And again, we've calculated the total molar mass of this compound. So if we multiply by 100%, we know that sulfur represents 10.3% of this compound. Similarly, the percentage of oxygen is 63.996 grams, which we obtained by multiplying 4 times the molar mass of oxygen divided by the total mass of the compound times 100, and we get that this compound is 20.5% oxygen. Now let's look at the next example. Calculate the mass percentage of water in zinc sulfate. And this is this kind of a compound is called a hydrate. Right? So we have hydrated zinc sulfate. If it weren't hydrated, we would call it anhydrous. So this hydrated zinc sulfate, is a substance that contains water in it. So for every mole of zinc sulfate, there are 7 moles of water. All right, so what do we know? We know our formula for hydrated zinc sulfate, so we can figure out the molar mass. And then we can figure out the percentage of water in this hydrated compound. All right, so the molar mass of hydrated zinc sulfate is equal to the mass of zinc plus the mass of sulfur plus 4 times the mass of oxygen plus 7 times 2 times the mass of hydrogen plus oxygen. Okay, this is not complicated math. You can do this. And if we just look at the mass of the total contributing mass of the water, of the 7 water molecules, that's 126.105 grams. And the total mass of the hydrated zinc sulfate is 287.541 grams. Thus, knowing the mass of the 7 moles of water for every mole of zinc sulfate and the total mass of the hydrated compound, we can determine the percent of water in this hydrated compound by simply taking the contributing mass of water over the total mass of the compound times 100, and we get that this is 43% water. Actually 43.9. So the percentage of water in the hydrated compound of zinc sulfate is 43.9%. All right, let's look at our next example. Magnesium hydroxide is 54.87% oxygen by mass. How many grams of oxygen are in 175 grams of compound? How many moles of oxygen is this? Okay, so we know that we have 175 grams of magnesium hydroxide. And that 54% of it, 54.87%, is oxygen. And we need to figure out how many grams of oxygen are in this 175 grams of magnesium hydroxide, and then how many moles of oxygen that's equal to. All right, so we know that the percentage of oxygen is equal to 54.87. And we know that is equal to the grams of oxygen over the total compound, grams, times 100%. Right? So that's percentage. So we can do, oops. So we can do just some algebraic math here, and we divide both sides by 100% and multiply both sides by 175 grams, right? So that we are left with 175 grams times 0.5487 will give us 96.02 grams of oxygen in these 175 grams of magnesium hydroxide. Knowing we have 96.02 grams of oxygen in this compound, we can figure out how many moles of oxygen we have. Knowing the molar mass of oxygen, right? That in every mole of oxygen, we have 15.999 grams of oxygen. So therefore, there are 6.00 moles of oxygen in 175 grams of magnesium hydroxide. 6 moles. The next concept that you need to wrap your head around is empirical versus molecular formulas. So the subscripts in the empirical formula of a compound represent the smallest whole number ratios between the elements of the compound. However, the empirical formula doesn't always correlate with the actual numbers of atoms present in the compound. For example, the empirical formula for the gas diborane, BH3, is BH3, but in reality the atoms combine as B2H6, which we refer to as the molecular formula. In this case, the ratio of atoms in the molecular formula compared to the empirical formula is 2. So if we were to multiply BH3 by 2, we would get B2H6. All right, so the empirical formula can be determined by knowing the percent composition of the compound, and then the molecular formula of a compound can be determined by knowing the molecular formula mass. For example, a compound contains 32.38% sodium, 22.65% sulfur, and 44.99% oxygen. Find the empirical formula of this compound. So first you have to ask yourself, what do you know? You know the percentages of elements in the compound. And what do you need to find out? You want to find out the relative ratios of moles of sodium to sulfur to oxygen in the compound. So you're trying to find the minimum ratio of those subscripts. In a 100-gram sample of this compound, you know that you would have 32.8 grams of sodium, right? Because of the percentage here. You know that there'd be 22 grams of sulfur because of this percentage. And you know that there are 44.99 grams of oxygen because of that percentage, right? In 100 grams. So you can calculate the moles, the relative moles of each element, knowing, of course, the molar mass of each element. So 32.38 grams of sodium times 1 mole of sodium per every 22.99 grams of sodium gives us 1.48 moles of sodium. We do the same thing with sulfur and oxygen to get these mole values. And now we want to determine the smallest whole number ratio of the atoms by dividing each number by the smallest number of the group. So in this case, the smallest number is the 0.7063 moles of sulfur. So we take 1.4 moles of sodium divided by that small number, we take the small number 0.7063 divided by itself, and then we take the moles of oxygen, 2.182 moles divided by the 0.7063. And these are the ratios that we get. 1.993 moles of sodium to 1 mole of sulfur to 1 mole, or to 3.98 1 moles of oxygen. And what we do is we round to the nearest whole number, right? So 1.993 rounds up to 2, 1 of course is 1, and 3.981 rounds up to 4. So we get the empirical formula of sodium sulfate. You can check your work by calculating the percent composition of each element in sodium sulfate based on this formula to see if it comes close to the experimental values, right? Which were, so, and you should know how to do that. So what is the percent sodium in this compound? Well, you know, sodium is 45.98, and you can calculate the total molar mass of sodium sulfate to be 142.0.36. So you get 32.37% sodium, which is relatively close to the experimental value that was given you. If you do the same thing for sulfur, you take the molar mass of sulfur divided by the total mass of the compound times 100%, and you get 22.57% sulfur, which is relatively close to the experimental value that was given you. And finally, you can do the same thing for oxygen, which there are 4 oxygens, so the total contributing mass of oxygen is 63.996 grams. The total compound, as we know, is 142.06 grams times 100%. So we get 45.06% oxygen, which is pretty close to the experimental value. So our calculation of the empirical formula being Na2SO4 has been checked. So we've done this correctly. So now let's look at our other example. Analysis of a 10.15 gram sample of a compound known to contain only phosphorus and oxygen indicates a phosphorus content of 4.433 grams. So what is the empirical formula of this compound? Again, you first want to ask yourself, what do you know? You know that you have a compound with only phosphorus and oxygen, and that there are 4.433 grams of phosphorus in a 10.15 gram sample of this compound. So you can figure out the mass of oxygen just from that information. And you would do that by simply taking the total mass of the sample, subtracting the mass of phosphorus, and then you're left with the mass of oxygen, which would be 5.717 grams. All right, so now you have the grams of oxygen, and you want to figure out the empirical formula, or the relative molar ratios of phosphorus and oxygen in this compound. So you want to determine the composition in moles. So you want to convert these gram numbers into moles. So you know you have 4.433 grams of phosphorus, and you know there are 30.5797 grams of phosphorus in every mole. So you get a mole amount of 0.1431 moles of phosphorus in this sample. You do the same thing for oxygen, and you get 0.3547 moles of oxygen. So we want to determine the smallest whole number ratio of the atoms by dividing each number by the smallest number in the group, like we did before. So if we take 0.1431 divided by 0.1431, of course we'll get 1. And if we take 0.3547 and divide it by 0.1431, we get 2.497. And that's not near enough to a whole number that we can just round up or down. So what we'll do in this case is try multiplying by additional values until we get whole numbers. So if we multiply both by 2, we can get 2 for phosphorus, and we get 4.994 for oxygen, which can be rounded up to 5, giving us the empirical formula of P2O5. Okay? All right, let's keep going. Okay, this is our last example, and this helps you understand how you can get a molecular formula from the empirical formula and knowing the molar mass of the compound. All right? Of the molecular compound. So here's our example. Analysis of the compound P2O5 indicates that a molar mass of the compound is 283.89 grams. What is the compound's molecular formula? Okay, so what do we know? We know the empirical formula and we know the molecular formula mass. And we want to find out what is the molecular formula. And as I've already implied to you, the empirical formula times the multiplying factor, which we're trying to figure out, will give us the molecular formula mass. So just converting this to an algebraic formula, the multiplying factor that we're looking for, x, is the molecular formula mass divided by the empirical formula mass. All right, do you remember how to find the molecular mass of P2O5? So P2O5 is equal to 2 times 30.974 grams for phosphorus plus 5 times 15.999 grams of oxygen, right, which gives us a total value of 141.94 grams for the empirical formula mass of P2O4. So now the only thing we have to do is take this number and insert it into our formula, right, where we've been given the molecular formula mass divided by the empirical formula mass gives us a factor of 2. So now all we have to do is multiply the empirical formula by 2 and we get the molecular formula. So now you are ready to tackle the practice questions. And I know that you can do these. All right, see you soon. Bye.